Imagine standing at the edge of an abyss so vast that all of human knowledge, every discovery we've ever made, every equation we've solved, every star we've mapped, amounts to nothing more than a single grain of sand on an endless beach. Now imagine that this abyss isn't just large, it's infinite. It doesn't just stretch beyond what we can see, it extends beyond what we can even comprehend. And here's what should truly terrify you, or perhaps fill you with wonder. Despite centuries of brilliant minds dedicating their entire lives to understanding the cosmos, despite our most powerful telescopes peering billions of light years into space, despite our most sophisticated theories that can predict the behavior of subatomic particles with astounding precision, we have only just begun to scratch the surface. In fact, the more we discover about the universe, the more we realize how little we actually know. It's as if every answer we find opens 1,000 new questions, each more perplexing than the last. Right now, at this very moment, you are traveling through space at over 1.3 million miles per hour. You can't feel it, but you're spinning with Earth's rotation, orbiting the Sun, moving with the solar system around the Milky Way, and hurtling through the cosmic void as our galaxy races toward an unknown destination in space. And yet, despite all this motion, despite all our sophisticated instruments, there are fundamental questions about the very fabric of reality that continue to elude the greatest scientific minds of our time. Questions so profound that they challenge everything we think we know about existence itself. What if I told you that everything you've ever seen, every star in the night sky, every planet, every galaxy, every atom in your body, every particle of matter that we've ever detected or measured, accounts for less than 5% of what actually exists in the universe? What if I told you that 95% of the cosmos is made of something we cannot see, cannot touch, cannot directly detect, and barely understand? What if the universe you think you know is just a tiny, almost insignificant fraction of what's really out there? Take a moment and ask yourself this. When you look up at the night sky, what are you really seeing? Are you looking at reality, or just the visible tip of an incomprehensible cosmic iceberg? This isn't science fiction. This isn't speculation. This is the startling reality that astronomers and physicists confront every single day. And tonight, we're going to journey together through the greatest mysteries that continue to baffle the scientific community, the profound unknowns that represent the frontiers of human knowledge, the cosmic puzzles that keep astronomers awake at night, wondering if we'll ever truly understand the universe we call home. Let's begin with perhaps the most humbling mystery of all, one that fundamentally changed how we see the universe and revealed just how blind we've been. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a group of over 1,000 galaxies located about 300 million light-years from Earth. Zwicky was measuring how fast these galaxies were moving, and what he discovered didn't make any sense. The galaxies were moving so fast that they should have been flying apart. The visible matter in these galaxies, all the stars and gas and dust that he could observe, didn't produce nearly enough gravitational pull to hold them together at those speeds. According to the laws of physics, the cluster should have torn itself apart billions of years ago. But it hadn't. Something was holding it together. Zwicky proposed something radical. There must be matter we cannot see, invisible matter that doesn't emit, absorb, or reflect light, but still exerts gravitational force. He called it dark matter, and his colleagues largely dismissed the idea. It seemed too strange, too convenient. Perhaps there was an error in his calculations, they thought. Perhaps he had misunderstood something. But Zwicky was right. Decades later, in the 1970s, astronomer Vera Rubin made observations that would cement dark matter as one of the greatest mysteries in science. She was studying spiral galaxies, measuring how fast stars orbit around the galactic center at different distances. According to Newton's laws of motion and our understanding of gravity, stars farther from the center should orbit more slowly than stars closer to the center, just like planets farther from the Sun take longer to complete their orbits. But that's not what Rubin found. Instead, she discovered that stars on the outer edges of galaxies were moving just as fast as stars closer to the center. This was impossible unless there was far more mass in these galaxies than we could see. The implications were staggering. Galaxies must be embedded in enormous halos of invisible matter, matter that outweighs all the visible stars, planets, and gas by a factor of 6 to 1. This dark matter makes up approximately 27% of the universe's total mass energy content, and we have absolutely no idea what it is. Think about that for a moment. Nearly a third of everything that exists in the universe is made of something completely unknown to science. It's not regular matter made of atoms like you and me. It doesn't interact with light in any way. It passes through ordinary matter as if it weren't even there. Right now, billions of dark matter particles are probably streaming through your body, through the Earth, through everything, without leaving the slightest trace. Scientists have proposed numerous candidates for what dark matter might be. Perhaps it's made of exotic particles called WIMPs, which stands for weakly interacting massive particles. Perhaps it's axions, hypothetical particles that are incredibly light and barely interact with anything. Perhaps it's primordial black holes, formed in the first moments after the Big Bang. Perhaps it's something we haven't even imagined yet. Deep underground, in laboratories shielded from cosmic rays and other interference, scientists have built incredibly sensitive detectors hoping to catch a dark matter particle interacting with normal matter. These experiments have been running for years. So far, they've found nothing definitive. Dark matter remains as elusive as ever, a cosmic ghost that shapes the structure of the universe while remaining invisible to our most sophisticated instruments. But here's what makes this even more mysterious. We can map dark matter. We can see its effects. When light from distant galaxies passes through regions of space containing dark matter, the gravitational field of the dark matter bends the light, creating distortions we can measure. This effect, called gravitational lensing, allows us to create maps showing where dark matter exists in the universe. And what these maps reveal is extraordinary. Dark matter forms a vast cosmic web, invisible filaments stretching across hundreds of millions of light years, connecting galaxy clusters like neural pathways in a cosmic brain. Visible matter, all the galaxies and stars we can see, is merely trapped along these invisible strands like dewdrops on a spider's web. Ask yourself this: how can we live in a universe where we don't even know what most of it is made of? How can we claim to understand reality when 70% of the cosmos consists of things we've never identified? Because dark matter isn't even the strangest part. Not by a long shot. In 1998, two teams of astronomers were studying distant supernovae, using them as cosmic distance markers to measure the expansion of the universe. They expected to find that the universe's expansion was slowing down over time, decelerated by the gravitational pull of all the matter in the cosmos. Instead, they discovered something that shocked the scientific community to its core. The universe's expansion is speeding up. Not slowing down, but accelerating faster and faster with each passing moment. This discovery was so unexpected, so contrary to everything we thought we knew, that both teams checked and rechecked their data multiple times, certain they had made a mistake. But they hadn't. The universe is accelerating, driven by something that works in the opposite way to gravity, something that pushes rather than pulls, something that fills the empty space between galaxies and drives them apart at an ever-increasing rate. Scientists call this mysterious force dark energy, and it's even more perplexing than dark matter. While dark matter at least behaves somewhat like regular matter in that it exerts gravitational attraction, dark energy is something entirely different. It appears to be a property of space itself, a cosmic pressure that becomes stronger as the universe expands and creates more space. The more space there is, the more dark energy there is, and the faster the expansion accelerates. Dark energy makes up approximately 68% of the universe. Let that sink in. More than 2/3 of all the energy in existence is in a form we don't understand, can't directly detect, and can barely theorize about. One possibility is that dark energy is the cosmological constant, a concept that Albert Einstein introduced and later called his greatest blunder. Einstein's equations of general relativity suggested that the universe should be either expanding or contracting, but at the time, everyone believed the universe was static and eternal. So Einstein added a term to his equations, the cosmological constant, to balance the attractive force of gravity and keep the universe still. When Edwin Hubble discovered that the universe was actually expanding, Einstein abandoned the cosmological constant. But now it's back, potentially representing a fundamental energy of empty space itself. Quantum physics suggests that the vacuum of space isn't truly empty. Instead, it seethes with virtual particles that pop in and out of existence in accordance with Heisenberg's uncertainty principle. This quantum foam might give space itself an inherent energy. However, when physicists calculate what this vacuum energy should be, they get an answer that's wrong by a factor of 10 to the power of 120. That's not just wrong, that's the worst prediction in the history of physics. The calculated value is so large that the universe would have torn itself apart in an instant. Clearly, something is profoundly wrong with our understanding. Another possibility is that dark energy isn't constant at all, but changes over time. Perhaps it's a new type of energy field called quintessence that evolves as the universe ages. Or perhaps our understanding of gravity itself is incomplete, and on cosmic scales, gravity behaves differently than Einstein predicted. The truth is, we simply don't know. And the implications of dark energy are genuinely mind-bending. If dark energy continues to accelerate the universe's expansion, then eventually, billions of years from now, galaxies beyond our local group will recede from us faster than the speed of light. Not because they're moving through space that fast, but because space itself is expanding that rapidly. These galaxies will disappear beyond a cosmic horizon, their light redshifted into invisibility. Eventually, observers in the far future will look up at the night sky and see only the stars in their own galaxy. The rest of the universe will have vanished, carried away by the relentless acceleration of dark energy. Those future astronomers will have no way of knowing that billions of other galaxies once existed. The cosmic evidence of the Big Bang itself will be stretched beyond detection. In effect, the universe is erasing its own history. Now pause and consider. If we were living in that distant future, we would never have discovered the Big Bang. We would never have known about cosmic expansion. We would have formulated entirely different theories about the universe based on the limited evidence available to us. How many discoveries are we missing right now because the evidence has already been erased by cosmic time? What fundamental truths about reality remain hidden because we're looking at the universe too late or too early in its history? Speaking of the Big Bang, let's talk about what might be the most profound question humans have ever asked. What came before? The Big Bang Theory tells us that approximately 13.8 billion years ago, the universe began as an infinitesimally small point of infinite density and temperature, and then expanded rapidly into the cosmos we see today. We have remarkable evidence for this. The cosmic microwave background radiation, a faint afterglow of the Big Bang that permeates all of space, the fact that the universe is expanding, the abundance of light elements like hydrogen and helium that match the theory's predictions, and the large-scale structure of galaxies and galaxy clusters that formed from tiny quantum fluctuations in the early universe. But here's the problem. The Big Bang Theory describes what happened after the universe began, not what caused it to begin or what, if anything, existed before. When we try to trace the expansion backwards in time, our physics breaks down at a point called the Planck epoch, about 10 to the negative 43 seconds after the Big Bang. Before that moment, the universe was so small, so dense, and so hot that quantum effects dominated gravity, and we need a theory of quantum gravity to understand what happened. But we don't have a working theory of quantum gravity. So when people ask, what came before the Big Bang? The honest answer is, we don't know. We might never know. Some physicists argue that the question itself is meaningless. If time itself began with the Big Bang, if time is a property of our universe that came into existence along with space, matter, and energy, then there is no before. Asking what came before the Big Bang would be like asking what's north of the North Pole. It's a grammatically correct question that has no answer because the premise doesn't make sense. But other physicists aren't satisfied with that answer. They propose various scenarios for what might have preceded our universe. Perhaps our universe emerged from a previous universe that collapsed in a big crunch, bouncing back in an endless cycle of expansion and contraction. Perhaps our universe is just one bubble in an eternally inflating multiverse, where countless other universes are constantly forming from quantum fluctuations. Perhaps time does extend before the Big Bang, and our universe emerged from a pre-existing quantum state that we simply can't observe. One particularly fascinating idea is that the Big Bang wasn't the beginning of everything, but rather a phase transition, similar to how water turns to ice. Perhaps there was a previous state of existence with different laws of physics, and the Big Bang was the moment when those laws transformed into the ones we know today. Another profound mystery tied to the Big Bang is the incredible fine-tuning of the universe's fundamental constants. The laws of physics are governed by certain numbers, like the strength of gravity, the mass of the electron, and the speed of light. These numbers appear arbitrary. We don't know why they have the values they do, but if they were even slightly different, the universe would be radically different, and life as we know it could not exist. For example, if the strong nuclear force that holds atomic nuclei together were just 2% stronger, protons would have fused into heavier elements during the Big Bang, and hydrogen would be rare. Without abundant hydrogen, stars couldn't form the way they do, and life would be impossible. If it were 2% weaker, atomic nuclei wouldn't hold together, and complex chemistry couldn't exist. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars wouldn't form at all. If the cosmological constant that drives dark energy were larger by even a tiny amount, the universe would have expanded so rapidly that matter couldn't clump together to form galaxies and stars. The universe seems precisely calibrated to allow for the existence of complexity and life. Why? Is this just an incredible coincidence? Is there some deeper principle that requires these constants to have these specific values? Or are we living in a multiverse where every possible combination of physical constants exists somewhere, and we inevitably find ourselves in a universe capable of supporting our existence because we couldn't exist in any other kind? This last idea is called the anthropic principle, and it's deeply controversial. Some scientists find it philosophically unsatisfying, a non-explanation that amounts to saying, things are the way they are because if they weren't, we wouldn't be here to ask about it. Others argue it's a legitimate scientific hypothesis if the multiverse actually exists. Ask yourself, why do the laws of physics exist at all? Why is there something rather than nothing? Why is the universe comprehensible, governed by mathematical laws that we can discover and understand? These questions take us to the edge of science and philosophy, to the boundary where empirical investigation meets metaphysical speculation. And they highlight just how much we still don't know about the most basic aspects of existence. Let's turn our attention to objects so extreme that they represent a complete breakdown of our understanding of physics. Black holes. For most people, black holes are already mysterious, objects with gravity so strong that nothing, not even light, can escape. But the real mysteries run far deeper. Black holes represent places where Einstein's general relativity, our best theory of gravity, predicts its own failure. At the center of every black hole lies a singularity, a point where density becomes infinite and the curvature of spacetime becomes infinite. Our equations literally produce infinities and nonsense. This is physics' way of telling us that we're missing something fundamental. One of the greatest puzzles involving black holes is the information paradox. According to quantum mechanics, information cannot be destroyed. If you know the exact state of a system at one time, you can theoretically calculate what it was before and what it will be in the future. Information is preserved. But what happens when something falls into a black hole? For decades, physicists believed that anything crossing a black hole's event horizon was lost forever, along with all information about its quantum state. But in the 1970s, Stephen Hawking discovered that black holes aren't completely black. Due to quantum effects at the event horizon, black holes emit radiation, now called Hawking radiation. This radiation causes black holes to slowly evaporate over immense timescales. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate completely, far longer than the current age of the universe. But eventually, it would disappear, and apparently, all the information about everything that ever fell into it would be destroyed. This creates a paradox because it violates the fundamental principle that information is conserved. Hawking wrestled with this paradox for decades. Eventually, he came to believe that information must somehow be preserved in Hawking radiation, encoded in subtle correlations that we don't yet understand. But exactly how this happens remains one of the deepest mysteries in theoretical physics. Some physicists propose that information is encoded on the event horizon itself, in what's called a holographic principle. Just as a two-dimensional hologram can encode three-dimensional information, perhaps the two-dimensional surface of a black hole's event horizon encodes all the information about its three-dimensional interior. This idea has profound implications, suggesting that our entire universe might be a holographic projection, that the three dimensions we experience might be encoded on a two-dimensional surface at the cosmic boundary. Does that sound like science fiction? It's an active area of research, and many theoretical physicists take it seriously. Another mystery involves what happens if you actually fall into a black hole. According to general relativity, if you cross the event horizon of a sufficiently large black hole, you wouldn't immediately notice anything unusual. You would pass through the event horizon and have several hours or even days before being torn apart by tidal forces as you approach the singularity. From your perspective, space and time would behave strangely, but you wouldn't hit a wall or burn up at the event horizon. However, quantum field theory suggests something different. Some calculations indicate that the event horizon might be a firewall, a region of incredibly high energy that would incinerate anything trying to cross it. This contradicts general relativity's prediction of a smooth horizon. So which is right? Can both of our most successful theories be telling us conflicting things about the same phenomenon? This conflict highlights a fundamental problem. General relativity and quantum mechanics, the two pillars of modern physics, are incompatible. General relativity beautifully describes gravity and the large-scale structure of spacetime. Quantum mechanics perfectly describes the behavior of particles and forces at the smallest scales. Both theories have been tested countless times and have never been proven wrong within their domains. But when we try to apply both theories simultaneously, in situations involving both extreme gravity and quantum scales, like the singularity inside a black hole or the first moments of the Big Bang, they give contradictory results. We need a theory of quantum gravity, a framework that reconciles these two pillars of physics. String theory is one candidate. It proposes that fundamental particles aren't point-like objects but tiny vibrating strings, and that the universe has additional dimensions beyond the three of space and one of time that we experience. Loop quantum gravity is another approach, suggesting that space itself is quantized, made of discrete units rather than being infinitely divisible. But here's the problem. We have no experimental evidence for either theory. String theory makes predictions that we can't currently test because they involve energies far beyond what our particle accelerators can achieve. Loop quantum gravity faces similar challenges. We're in the unusual position of having multiple theoretical frameworks that might be correct, but no way to determine which, if any, actually describes reality. Think about what this means. We cannot fully understand black holes, the Big Bang, or the fundamental nature of space and time until we solve this problem. We're missing a crucial piece of the puzzle, and we don't know how to find it. Now, while we're on the subject of things we don't understand, let me ask you this. What is time? You might think that's a simple question with an obvious answer. Time is what clocks measure. It's the progression from past to present to future. It's the fourth dimension. But when you dig deeper, time becomes profoundly mysterious. Einstein's relativity taught us that time is relative, that it flows at different rates depending on your motion and the strength of the gravitational field you're in. An astronaut orbiting Earth ages slightly slower than people on the ground. Time near a black hole passes much more slowly than time far away. This has been experimentally verified countless times. GPS satellites have to account for relativistic time dilation, or they would quickly become inaccurate. But relativity describes how time behaves, not what time actually is. At the deepest level, our best theories of physics treat past, present, and future as equally real. The equations of physics work just as well going backwards in time as forwards. And yet, we experience time as flowing in one direction. We remember the past, but not the future. Eggs break, but don't unbreak. Stars shine energy into space, but don't absorb it. The universe clearly has an arrow of time. This arrow seems to be connected to entropy, the tendency of systems to move from ordered states to disordered states. A broken egg has higher entropy than an intact egg. Heat flows from hot objects to cold objects, increasing total entropy. The second law of thermodynamics says that the entropy of a closed system always increases over time. This gives time a direction. But here's the puzzle. The fundamental laws of physics are time reversible. If you watch a film of particles bouncing off each other, you can't tell if the film is running forwards or backwards because the laws governing their motion work the same in both directions. So where does the arrow of time, the increase of entropy, come from? The answer seems to be that the early universe was in an incredibly low entropy state. The Big Bang started with matter and energy distributed much more evenly and orderly than you'd expect by chance. As the universe evolved, entropy increased, giving time its arrow. But this just pushes the mystery back a step. Why did the universe begin in such a low entropy state? What set up those initial conditions? We don't know. Some physicists, including Julian Barber, have proposed even more radical ideas. Perhaps time doesn't exist at all at the fundamental level. Perhaps time is an emergent property, something that arises from more basic timeless laws, the way wetness emerges from water molecules even though individual molecules aren't wet. Perhaps the flow of time is an illusion created by our consciousness. These ideas challenge our most basic intuitions about reality. If time doesn't fundamentally exist, what does that mean for cause and effect? For the notion that the future is open and the past is fixed? For free will and choice? Consider this question. Do you experience time passing, or do you experience a series of moments, with your memory creating the illusion of flow? Let's shift gears and talk about a cosmic mystery that's causing heated debates right now: the Hubble tension. The Hubble constant is a number that describes how fast the universe is expanding. It's named after Edwin Hubble, who discovered that distant galaxies are moving away from us, with more distant galaxies moving faster. The Hubble constant tells us the expansion rate, how much faster galaxies recede for every additional megaparsec of distance. Measuring this number accurately is crucial because it helps us determine the age of the universe, its size, its fate, and tests the validity of our cosmological models. And here's the problem. Different measurement methods are giving us different answers, and the discrepancy is too large to be explained by random error. When astronomers measure the Hubble constant using the cosmic microwave background, the afterglow of the Big Bang, they get one value. When they measure it using nearby supernovae and other distance indicators, they get a different value, about 9% higher. 9% might not sound like much, but in cosmology, where measurements are incredibly precise, this discrepancy is enormous. It's statistically significant enough that it can't be dismissed as a measurement error. This tension suggests one of several possibilities, all of them profound. Perhaps one of the measurement methods has a systematic error we haven't identified. Perhaps dark energy isn't constant but changes over time. Perhaps there's new physics we haven't discovered, some additional component of the universe, or some modification to general relativity. Perhaps our entire cosmological model is wrong. This is why scientists are so excited and frustrated by the Hubble tension. If it's real, if both measurements are correct, then we're missing something fundamental about how the universe works. Resolving this mystery could lead to revolutionary discoveries. Another cosmic enigma that has astronomers puzzled is fast radio bursts, or FRBs. These are incredibly intense pulses of radio waves that last just milliseconds but release as much energy as the sun emits in days or even years. They come from distant galaxies, billions of light years away, and most of them have been detected only once, never to repeat. The first FRB was discovered in 2007 by astronomer Duncan Lorimer, who was analyzing archival data from the Parkes Observatory in Australia. The burst, later called the Lorimer burst, had occurred in 2001 but went unnoticed until Lorimer's analysis. It was so bright and so brief that initially, many astronomers suspected it was terrestrial interference or a glitch in the equipment. But FRBs kept appearing. By now, hundreds have been detected. Most happen once and never repeat, but a few sources produce multiple bursts. In 2020, for the first time, astronomers detected an FRB originating from within our own galaxy, the Milky Way, and they pinpointed its source. A magnetar, a type of neutron star with an incredibly powerful magnetic field. This discovery was exciting because it suggested a potential explanation for at least some FRBs. Magnetars are the most magnetic objects known in the universe, with magnetic fields trillions of times stronger than Earth's. Under certain conditions, they can release enormous amounts of energy in sudden outbursts. Perhaps FRBs are produced by magnetar flares. But here's the mystery. Not all FRBs seem to be consistent with the magnetar explanation. Some are too energetic. Some have properties that don't match what we'd expect from magnetars. Some come from galaxies where we wouldn't expect to find magnetars. The repeating FRBs are particularly puzzling because they show complex patterns that we don't understand. Some astronomers have speculated, though this is highly unlikely, that FRBs could be artificial signals from advanced civilizations. After all, they're brief, intense, and follow patterns we don't fully comprehend. However, most scientists think natural explanations are far more probable. The universe is full of extreme phenomena we don't yet understand, and FRBs are likely another example. The point is this: we're detecting powerful cosmic events billions of light years away, and we don't know what most of them are. Our universe is full of phenomena that defy our current understanding. Let me ask you something. Have you ever looked up at the night sky and wondered if anyone is looking back? The question of whether we're alone in the universe is one of the most profound mysteries in all of science. With trillions of stars in our galaxy alone and billions of galaxies in the observable universe, it seems statistically impossible that Earth is the only place where life has emerged. And yet, we have never detected any definitive sign of extraterrestrial life. This contradiction is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If intelligent civilizations are common in the galaxy, some of them should be millions or billions of years more advanced than us. They should have colonized the galaxy by now. We should see evidence of their existence. Megastructures harnessing the energy of stars, radio signals, signs of astroengineering projects. But we see nothing. Numerous explanations have been proposed. Perhaps intelligent life is extremely rare, arising only under very specific conditions that rarely occur. Perhaps life is common, but intelligence is rare. Perhaps civilizations inevitably destroy themselves before they can spread across the stars, falling victim to nuclear war, environmental collapse, or some other catastrophe. Perhaps advanced civilizations hide deliberately, avoiding contact with younger species. Perhaps they're here, but we don't recognize them because their technology is so advanced it's indistinguishable from natural phenomena. Perhaps interstellar travel is fundamentally impossible, limited by the laws of physics in ways we don't yet appreciate. One particularly unsettling idea is the Great Filter hypothesis. It suggests there's some extremely difficult step in the evolution from simple matter to spacefaring civilization, a filter that almost no species passes through. The question is the Great Filter behind us or ahead of us? Have we already passed the most difficult step, meaning we might be one of the very few species to make it this far? Or is the filter still in our future, Some catastrophic challenge that destroys almost every civilization before it can spread to the stars? We don't know. And that uncertainty has profound implications for humanity's future. Recent discoveries have made the question of extraterrestrial life more urgent and more tantalizing. We now know that planets are common. Nearly every star has planets orbiting it. We've discovered thousands of exoplanets, and many of them are rocky worlds in their star's habitable zone, where liquid water could exist on the surface. Some of these worlds might have conditions suitable for life. Moreover, we've discovered that life on Earth is far more resilient than we once thought. We've found microorganisms thriving in boiling acid, in frozen Antarctic lakes, deep underground, and in the radioactive environment inside nuclear reactors. Life adapts to almost any environment where liquid water exists and energy is available. This suggests life might be hardy and adaptable throughout the universe. We've also discovered that the building blocks of life are common in space. Amino acids, the components of proteins, have been found in meteorites and in interstellar clouds. Organic molecules exist throughout the cosmos. The chemistry of life isn't special to Earth. And yet, we haven't found life elsewhere. We've studied Mars extensively and found no definitive evidence of past or present life, though we're still looking. We've found that some moons in our solar system, like Europa, Enceladus, and Titan, might have subsurface oceans where life could potentially exist. But we haven't sent missions capable of detecting life to these worlds yet. The search continues. Radio telescopes scan the sky for signals from extraterrestrial civilizations. New telescopes study the atmospheres of exoplanets, looking for biosignatures, gases that might be produced by living organisms. Rovers explore Mars. Missions are being planned to the icy moons of Jupiter and Saturn. But as of now, we remain alone, as far as we can tell. And the silence is deafening. Ask yourself this: would you prefer to discover that we're alone in the universe, or that we're not? What would it mean for humanity if we found out we're the only intelligent life in the cosmos? What would it mean if we discovered we're not? Now let's discuss one of the strangest and most counterintuitive aspects of reality: quantum mechanics. At the scale of atoms and subatomic particles, the universe behaves in ways that seem utterly bizarre compared to our everyday experience. Particles exist in multiple states simultaneously until observed. They can be in two places at once. They can pass through barriers they shouldn't be able to cross. Pairs of particles can be entangled so that measuring one instantly affects the other, even if they're on opposite sides of the universe. Electrons behave as both particles and waves, depending on how you observe them. These aren't just theoretical peculiarities. Quantum mechanics has been tested more rigorously than perhaps any other scientific theory. It works. The device you're using to listen to this, whether it's a phone, computer, or other electronic device, relies on quantum mechanics. Transistors, lasers, MRI machines, and countless other technologies exist because quantum mechanics accurately describes how nature works at small scales. But here's the profound mystery. We don't know what quantum mechanics means. We don't know what's actually happening. The standard interpretation, called the Copenhagen interpretation, says that particles exist in a superposition of all possible states until they're measured, at which point the wave function collapses and the particle takes on a definite state. But what counts as a measurement? What causes the collapse? Why does observation change reality? The Copenhagen interpretation essentially says, don't ask what's really happening, just use the math to make predictions. This deeply bothered many physicists, including Einstein, who famously said, "God does not play dice with the universe." Alternative interpretations have been proposed. The many worlds interpretation suggests that the wave function never collapses. Instead, every possible outcome of a quantum measurement actually occurs, but in different branches of reality. Every time a quantum event could go multiple ways, the universe splits into multiple versions, each experiencing a different outcome. In one branch, Schrödinger's cat is alive. In another, it's dead. Both outcomes happen, just in different universes that can't interact with each other. If the many worlds interpretation is correct, and we have no definitive way to prove or disprove it, then there are countless copies of you, living out every possible variation of your life based on different quantum outcomes. Another interpretation, called pilot wave theory or Bohmian mechanics, suggests that particles do have definite positions and velocities at all times, but they're guided by a quantum wave that we can't directly observe. In this view, quantum randomness isn't fundamental but arises from our ignorance of these hidden variables. The problem is that all these interpretations make the same predictions. They're empirically equivalent, at least with current experiments. So how do we choose between them? Is reality fundamentally random and probabilistic, or is there an underlying determinism we can't access? Do parallel universes exist, or is there just one reality? We don't know. And quantum mechanics gets even stranger when combined with relativity. Quantum field theory, which describes particles as excitations of underlying fields, has been spectacularly successful, giving us the standard model of particle physics, which accurately describes all known particles and forces except gravity. The standard model's predictions have been confirmed to extraordinary precision. It predicted the existence of several particles before they were discovered, including the Higgs boson, which was finally detected in 2012 at the Large Hadron Collider. But the standard model leaves many questions unanswered. Why are there 3 generations of particles? Why do particles have the masses they have? Why are there 4 fundamental forces and not a different number? What is the nature of neutrinos, mysterious particles that barely interact with matter and seem to have tiny but non-zero masses? Is there physics beyond the standard model? We have strong reasons to believe there must be physics beyond what we currently know. The standard model doesn't include gravity. It doesn't explain dark matter or dark energy. It doesn't explain why the universe has more matter than antimatter. That last point is particularly puzzling. According to our theories, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate, converting into pure energy. If the Big Bang created equal amounts, they should have annihilated each other, leaving a universe full of radiation but no matter. And yet, here we are, made of matter, living in a universe full of matter with barely any antimatter. There must be some asymmetry, some difference in how matter and antimatter behave, that caused a slight excess of matter in the early universe. The standard model includes mechanisms that could create such an asymmetry, but when physicists calculate how much asymmetry these mechanisms should produce, it's nowhere near enough to explain the universe we observe. So what created the matter-antimatter asymmetry? We don't know. It's one of the biggest unsolved problems in physics. Imagine if the answer turns out to be something completely unexpected, a new force or particle that we haven't even conceived of yet. How would that change our understanding of the universe? Let's talk about the large-scale structure of the universe, the cosmic web of galaxies, galaxy clusters, and vast voids that characterizes the cosmos on the largest scales. When you look at maps of galaxy distribution across billions of light years, you see a striking pattern. Galaxies aren't randomly scattered. They're organized into filaments and sheets surrounding enormous empty voids. It looks remarkably like a 3-dimensional spider web or the neural structure of a brain. Galaxy clusters sit at the intersections of filaments, connected by walls and sheets of galaxies, with vast voids in between containing almost nothing. This structure formed from tiny density fluctuations in the early universe. In the first moments after the Big Bang, quantum fluctuations created slight variations in density from place to place. Regions that were slightly denser had slightly stronger gravity and attracted more matter. Over billions of years, these tiny differences grew, with denser regions collapsing to form galaxies and clusters while less dense regions became voids. We can simulate this process on computers, starting with the initial conditions suggested by observations of the cosmic microwave background and letting the simulation evolve according to the laws of gravity and physics. Remarkably, these simulations produce structures that look very much like what we observe in the real universe. This is a triumph of cosmology and strong evidence that we understand the broad strokes of how the universe evolved. But mysteries remain. We don't fully understand how galaxies form. The simulations can show us where dark matter clumps together, but turning dark matter halos into galaxies full of stars, gas, and dust involves complex processes that are difficult to model accurately. How does gas cool and fall into the center of a dark matter halo? How do supermassive black holes form at the centers of galaxies? How do these black holes influence galaxy formation through their powerful jets and radiation? Why do galaxies have the range of shapes and sizes that we observe? One of the most perplexing discoveries in recent years involves the first galaxies. According to our models, the first stars and galaxies should have formed a few 100 million years after the Big Bang, growing gradually over time. But the James Webb Space Telescope, which started observations in 2022, has found galaxies that appear to be larger and more mature than expected at very early times in the universe's history. Some of these galaxies existed when the universe was only a few 100 million years old, yet they appear surprisingly massive and well-developed. This is causing astronomers to question their models. Perhaps galaxy formation happened faster than we thought. Perhaps there are processes we don't understand that allowed galaxies to grow more quickly in the early universe. Perhaps some of our assumptions about cosmology need to be revised. It's too early to say what these observations mean, but they're a reminder that the universe still has the capacity to surprise us. Another mystery involves the structures at the very largest scales. The cosmological principle, a fundamental assumption in cosmology, states that the universe should be homogeneous and isotropic on large enough scales, meaning it should look roughly the same in all directions and all places. And indeed, the cosmic microwave background is incredibly uniform, varying by only about 1 part in 100,000 across the sky. But some observations have challenged this assumption. Astronomers have found structures that seem too large to fit with our models of how structure forms. There's the Hercules Corona Borealis Great Wall, a structure of galaxy clusters spanning about 10 billion light-years, which is larger than what simulations suggest should exist. There's the cold spot in the cosmic microwave background, an unusually large cold region that might be a statistical fluke or might indicate something strange about that part of the universe. Some studies have suggested that the universe's expansion might not be perfectly uniform in all directions, that there might be a preferred direction, an axis of evil in the cosmic microwave background. However, these findings are controversial and not universally accepted. They might be statistical anomalies or the result of systematic errors in analysis. The point is, even our most basic assumptions about the universe being the same everywhere might need to be examined more carefully. Now, consider this question. Is the universe we observe, the patch of space extending about 46 billion light-years in all directions from us, all that exists? Or is it just a tiny portion of something much larger? The concept of the multiverse, the idea that our universe might be just one of many, has gained serious consideration among physicists, though it remains highly speculative and controversial. There are actually several different multiverse concepts. One arises from eternal inflation theory. Inflation is a period of exponential expansion that's believed to have occurred in the first tiny fraction of a second after the Big Bang, smoothing out the universe and explaining why it looks so uniform. Some versions of inflation theory suggest that inflation doesn't end everywhere at once. Instead, it ends in some regions, creating bubble universes like ours, while continuing elsewhere. In this scenario, countless bubble universes are constantly forming, each potentially with different physical laws and constants, existing in an eternally inflating superspace. Another multiverse concept comes from string theory, which suggests there might be something like 10 to the power of 500 different possible universes, each with different configurations of the extra dimensions that string theory predicts. This is called the string theory landscape, and it's so vast that every possible set of physical laws might be realized somewhere. The many worlds interpretation of quantum mechanics suggests yet another type of multiverse, where every quantum event spawns new branches of reality. Then there's the mathematical universe hypothesis proposed by cosmologist Max Tegmark, which suggests that every mathematically consistent structure exists physically as a universe somewhere. In this view, our universe is just one mathematical structure among infinitely many. The multiverse concept is appealing in some ways. It could explain the fine-tuning of physical constants. If countless universes exist with different values for these constants, it's not surprising that we find ourselves in one of the rare universes where the constants allow for life. It's an anthropic explanation. We observe this universe because we couldn't exist in the others. But the multiverse concept is also deeply troubling to many scientists. If other universes are forever beyond our ability to observe or interact with, are they even scientific? Science depends on testable predictions and empirical observation. If we can never observe other universes, how can we ever confirm or refute the multiverse hypothesis? Isn't it just metaphysical speculation dressed up in scientific language? Some physicists argue that the multiverse is a testable idea. Even if we can't observe other universes directly, the theories that predict them make other predictions we can test. If those theories are confirmed in their testable predictions, we gain confidence in their other predictions, including the multiverse. Others argue that accepting the multiverse represents a dangerous lowering of scientific standards, a retreat from demanding real explanations in favor of anything is possible somewhere. This debate gets to the heart of what we mean by scientific explanation and understanding. Is explaining our universe's properties by saying, we're one of countless universes with different properties, really an explanation? Or is it giving up on finding a deeper reason for why things are the way they are? These are questions without clear answers, and they highlight the boundaries of our knowledge. Let me pose this question to you. If you could know for certain whether other universes exist, would you want to know? What would it mean for our place in reality if we're not just one planet among trillions in our universe, but one universe among an infinity of others? Another profound mystery that astronomy intersects with, though it's more philosophical than purely scientific, is the question of consciousness and its role in the universe. Why do we have subjective experiences? Why is there something it feels like to be you? Your brain is made of atoms following the laws of physics, electrical signals, and chemical reactions cascading through neural networks. In principle, we could describe all of this objectively, mapping every neuron and synapse. But none of that description would capture what it feels like to experience the color red, to feel pain or joy, to have the sensation of being a conscious self. This is called the hard problem of consciousness, and we have no scientific explanation for it. We can study which brain regions are active during different experiences. We can identify neural correlates of consciousness. But we can't explain why those physical processes give rise to subjective experience. Some interpretations of quantum mechanics suggest consciousness plays a fundamental role in reality. In the Copenhagen interpretation, observation causes the wave function to collapse. But what counts as an observer? Does it require consciousness? Some physicists have suggested that consciousness is necessary to actualize definite outcomes from quantum possibilities. Other physicists strongly reject this idea, arguing that measurement and observation in quantum mechanics don't require consciousness, just interaction with a macroscopic system that destroys quantum coherence. A detector or even a speck of dust can collapse a wave function without any conscious observer being involved. But the questions persist. Is consciousness something special, a fundamental aspect of the universe like space, time, and matter? Or is it an emergent property of sufficiently complex information processing, no more mysterious than how wetness emerges from water molecules? Some theorists, like physicist Roger Penrose, have proposed that consciousness might involve quantum processes in the brain, that our subjective awareness arises from quantum effects in cellular structures called microtubules. If true, understanding consciousness might require understanding quantum gravity, the still elusive union of quantum mechanics and general relativity. Others propose panpsychism, the idea that consciousness is a fundamental property of all matter, that even electrons have some primitive form of experience. In this view, Human consciousness is what happens when you organize conscious matter into complex patterns. This sounds mystical, but some serious philosophers and scientists take it seriously because it might solve the hard problem by denying that consciousness needs to emerge from non-conscious matter. We simply don't know, and the mystery of consciousness connects to cosmology in strange ways. The universe existed for billions of years before consciousness emerged, at least on Earth. But in another sense, the universe's properties only became defined when consciousness appeared to observe them, at least according to some interpretations of quantum mechanics. There's also the simulation hypothesis, popularized by philosopher Nick Bostrom. He argues that if it's possible for advanced civilizations to create simulated realities, and if such civilizations would create many simulations, then statistically we're more likely to be living in a simulation than in base reality. After all, there would be one real universe but countless simulated ones. This hypothesis is difficult to test, though some physicists have proposed potential signatures that might indicate we're in a simulation, like finding evidence that space-time is discrete rather than continuous, or discovering limits to computational precision in physical laws. Whether you find these ideas intriguing or absurd, they highlight how the fundamental nature of reality remains mysterious. We don't know what consciousness is, where it comes from, or what role, if any, it plays in the cosmic scheme. Now let's turn to the ultimate question. What is the fate of the universe? Based on current observations, the universe will continue expanding forever, driven by dark energy. Over time, this expansion will accelerate, carrying distant galaxies beyond our cosmic horizon. But what happens in the very long term, over timescales of trillions and quadrillions of years? Eventually, star formation will end. Stars are born from clouds of gas and dust, primarily hydrogen and helium. They fuse this hydrogen into heavier elements, eventually dying and sometimes returning material to space in supernova explosions. But each cycle converts some hydrogen into helium and heavier elements that are harder to fuse. Eventually, in about 100 trillion years, the last stars will burn out. The universe will enter the degenerate era, dominated by dead stellar remnants, white dwarfs, neutron stars, and black holes. Over truly immense timescales, even these remnants will decay or disappear. Protons might decay, though we've never observed this. If they do, over timescales of 10 to the 34 years or longer, even white dwarfs and neutron stars will gradually dissolve into radiation and lighter particles. Black holes will evaporate through Hawking radiation. Stellar mass black holes will take 10 to the 67 years to evaporate. Supermassive black holes at the centers of galaxies, with masses billions of times that of the Sun, will take 10 to the 100 years or longer. Eventually, the universe will enter the black hole era, when black holes are the only significant structures remaining. And then, after they too evaporate, the dark era, an endless expanse of dilute radiation and isolated particles, spreading ever farther apart as space continues expanding. In this far future, the universe will be a cold, dark, nearly empty void. No stars will shine. No galaxies will exist. The temperature will approach absolute zero. Entropy will be at or near its maximum. This is sometimes called the heat death of the universe, the end state when all useful energy has been expended and no processes can occur. But even this might not be the end. Some speculations suggest that given infinite time, quantum fluctuations could spontaneously create new regions of space that begin inflating, forming new universes. This is called quantum tunneling or vacuum decay, and it's purely speculative, but it raises the possibility that even in the heat death scenario, the cosmos might not be truly dead. Another possibility is that the nature of dark energy might change. If dark energy increases over time rather than remaining constant, it could lead to a big rip, where the expansion eventually becomes so rapid that it tears apart galaxy clusters, then galaxies, then solar systems, then planets, then atoms themselves. This would occur in a finite time, perhaps tens of billions of years from now. Alternatively, if dark energy decreases or reverses, the universe could eventually stop expanding and begin contracting, leading to a big crunch where everything collapses back into a singularity, possibly followed by a big bounce that creates a new universe. This cyclic cosmology is an alternative to the single Big Bang followed by eternal expansion. The truth is, we don't know the universe's ultimate fate because we don't fully understand dark energy. Until we know what dark energy is and how it behaves over cosmic timescales, the long-term future remains uncertain. But all these scenarios assume our current understanding of physics is roughly correct. What if there are revolutions in physics still to come that completely change our picture of the universe? Think about this. Every time we've probed nature more deeply, we've discovered new layers of complexity. Atoms aren't fundamental. They're made of protons, neutrons, and electrons. Protons and neutrons aren't fundamental. They're made of quarks. Are quarks fundamental, or are they made of something even smaller, like strings or other structures we haven't discovered? Is space smooth and continuous, or is it made of discrete units at the Planck scale, about 10 to the negative 35 meters? Is space-time fundamental, or does it emerge from something more basic? These questions point to how much we still don't know about the very fabric of reality. Another mystery worth discussing is the nature of gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. Gamma-ray bursts release more energy in a few seconds than the Sun will emit in its entire 10 billion-year lifetime. They occur several times a day, scattered randomly across the universe, flashing into existence and fading away within seconds or minutes. For the brief time they're active, they can outshine all the other stars in the entire universe combined in gamma-ray light. We now believe that long-duration gamma-ray bursts, lasting more than 2 seconds, are produced by the collapse of massive stars, at least 30 times more massive than the Sun, into black holes. As the star's core collapses, it forms a rapidly rotating black hole or neutron star that launches powerful jets of material at nearly the speed of light. If one of these jets happens to be pointed at Earth, we see it as a gamma-ray burst. Short-duration gamma-ray bursts, lasting less than 2 seconds, are thought to be produced by the merger of 2 neutron stars or a neutron star and a black hole. In 2017, we observed both gravitational waves and electromagnetic radiation from a neutron star merger, confirming this connection. But many details remain mysterious. How exactly are the jets launched? What accelerates particles to such high energies? Why do some bursts have afterglows that last for weeks while others fade quickly? Do all massive star collapses produce gamma-ray bursts, or only special ones? Gamma-ray bursts are also potentially dangerous. If a gamma-ray burst occurred in our galaxy and was pointed at Earth, the intense radiation could strip away our ozone layer, exposing the surface to deadly solar ultraviolet radiation. Some scientists have speculated that a gamma-ray burst might have caused one of Earth's mass extinctions in the distant past, though there's no strong evidence for this. Fortunately, gamma-ray bursts are rare in any given galaxy, occurring perhaps once every few 100,000 years, and the chance of one being pointed at us is small. Still, it's a reminder that the universe contains processes powerful enough to threaten life on cosmic scales. There's also the mystery of cosmic rays, high-energy particles, mostly protons, that constantly bombard Earth from space. Most cosmic rays come from supernova remnants in our galaxy, but the highest energy cosmic rays, with energies 10 million times greater than anything we can produce in particle accelerators, must come from somewhere else. What could accelerate particles to such incredible energies? Perhaps supermassive black holes in the centers of active galaxies. Perhaps the collision of galaxy clusters. Perhaps something we haven't imagined. We don't know. Detecting where these ultra-high-energy cosmic rays come from is difficult because their paths are bent by magnetic fields in space, scrambling the information about their origins. Studying cosmic rays from space also raises philosophical questions. These particles have traveled for millions or billions of years across the cosmos to reach Earth. Some of them might be older than our solar system, carrying information about long-ago events in distant parts of the universe. In a sense, they're messages from the cosmos, if only we could fully decode them. let's discuss another profound unknown: the nature of space itself. We tend to think of space as a stage on which events occur, an empty container in which matter and energy exist. But Einstein's general relativity teaches us that space is dynamic, curved by matter and energy, stretching and warping in response to mass. Space isn't just a passive background, it's an active participant in physics. But what is space made of? Is it a substance, or is it nothing? If it's nothing, how can it stretch, curve, and carry waves in the form of gravitational radiation? Quantum field theory suggests that what we call empty space is actually seething with quantum fields. Every point in space is filled with electromagnetic fields, electron fields, quark fields, and fields for every other type of particle. These fields have ground states, their lowest energy levels, and particles are excitations or vibrations of these fields. But this raises new questions. Why do these fields exist? What determines their properties? Are fields fundamental, or are they made of something more basic? Some theories, like loop quantum gravity, propose that space itself is quantized, made of discrete units related to the Planck length. If true, zooming in far enough would reveal space to be grainy rather than smooth, made of tiny loops or other structures. String theory suggests that what we perceive as point particles are actually tiny vibrating strings, and that space has more dimensions than the three we experience. These extra dimensions are curled up so small that we can't perceive them directly, but they influence the properties of particles and forces. These ideas are speculative, but they highlight that we don't truly understand what space is at the deepest level. Similarly, we don't understand why the universe has the dimensionality it does. Why 3 dimensions of space and 1 of time? Mathematical consistency allows for universes with different numbers of dimensions. In some of these universes, physics would be impossible. For instance, in 2 spatial dimensions, you can't have complex structures like brains. In 4 more spatial dimensions, orbits are unstable and atoms can't exist in the form we know. So perhaps 3 spatial dimensions is special, necessary for complexity and life. But this still doesn't explain why our universe has this property. Is it fundamental, or is it accidental? One possibility in a multiverse of universes with different dimensionalities? These questions touch on the deepest aspects of reality, and we're far from answering them. Here's something to consider. If you could add one new sense to your human perception, one that revealed something about the universe we currently can't detect, what would you want it to be? The ability to see dark matter? To perceive other dimensions? To experience time as a dimension you could move through like space? Now let's talk about one of the most exciting recent developments in astronomy: the detection of gravitational waves. In 1915, Einstein's general relativity predicted that accelerating masses should produce ripples in spacetime itself, disturbances that travel at the speed of light and carry energy away from their source. These gravitational waves stretch and compress space as they pass through it, but the effect is incredibly tiny. Even waves from the most violent cosmic events change distances by less than the width of an atomic nucleus over distances of kilometers. For a century, gravitational waves remained undetected, a prediction of theory without experimental confirmation. Then, on September 14, 2015, the LIGO detectors in Louisiana and Washington state detected a signal, a pattern of stretching and compressing space that lasted a fraction of a second. The signal matched perfectly the predicted signature of 2 black holes, each about 30 times the mass of the Sun, spiraling together and merging 1.3 billion light-years away. This detection was revolutionary. It confirmed a major prediction of general relativity, proved that black holes exist and can merge, and it opened an entirely new way of observing the universe. Light and other electromagnetic waves have been our window to the cosmos for all of history. But gravitational waves provide completely different information. They're produced by the motion of massive objects, particularly in violent events like black hole mergers, neutron-star collisions, and supernovae. They pass through matter almost without interaction, so they carry information from regions that light can't escape, like the interiors of merging black holes. Since that first detection, dozens of gravitational wave events have been observed. Most are black hole mergers, but we've also detected neutron star mergers. Each detection teaches us something new about these extreme objects and the physics of strong gravity. But many mysteries remain. We've found that black holes merge more often than we expected, and that the merging black holes can be more massive than theoretical models predicted. This suggests we're missing something about how black holes form and evolve. There are also hints in the gravitational wave data of a stochastic background, a constant hum of gravitational waves from countless distant sources throughout the universe, overlapping into a steady signal. Detecting and analyzing this background could reveal information about the early universe and processes we can't observe any other way. Future gravitational wave detectors, both on Earth and in space, will be far more sensitive and able to detect a wider range of frequencies. They might observe gravitational waves from the Big Bang itself, carrying information about the first moments of the universe's existence. They might detect waves from cosmic strings, hypothetical defects in space-time left over from phase transitions in the early universe. They might reveal entirely new types of objects and phenomena we haven't imagined. Gravitational wave astronomy is still in its infancy, and it represents one of the most promising frontiers for future discoveries. Another recent breakthrough is the imaging of black holes. In 2019, the Event Horizon Telescope, a global network of radio telescopes working together to create an Earth-sized virtual telescope, produced the first image of a black hole shadow. The target was the supermassive black hole at the center of the galaxy M87, located about 55 million light-years away and containing 6.5 billion times the mass of the Sun. The image shows a dark shadow surrounded by a bright ring of glowing matter. The shadow is larger than the black hole's event horizon because light passing near the black hole gets bent by gravity, creating a dark region larger than the horizon itself. This image confirmed predictions of general relativity in one of the most extreme environments in the universe. In 2022, the Event Horizon Telescope revealed an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy, about 4 million times the mass of the Sun and only 26,000 light-years away. This image was harder to produce because Sagittarius A star is much smaller and its surrounding matter changes on timescales of minutes, like trying to photograph a child who won't sit still. These images are scientific and cultural achievements, visual proof of objects so extreme that they were once thought to be mathematical curiosities that couldn't exist in nature. But they also raise questions. We still don't fully understand how supermassive black holes form. The black holes at galaxy centers are millions or billions of times more massive than the Sun. How did they grow so large? Did they form from the collapse of giant stars in the early universe and then grow by consuming matter over billions of years? Did they form directly from the collapse of giant gas clouds? Did smaller black holes merge to form them? Observations from the James Webb Space Telescope have found supermassive black holes existing when the universe was less than 1 billion years old. This is puzzling because it's not clear how black holes could grow so large so quickly. Either they formed from much more massive seeds than we thought, or they grew faster than our models predict, or both. Understanding supermassive black holes is crucial because they play a major role in galaxy evolution. The jets and radiation they produce when consuming matter can heat and push away gas, regulating star formation in galaxies. There's a tight correlation between the mass of a galaxy's central black hole and properties of the galaxy's bulge, suggesting they evolved together. But the details of this coevolution remain mysterious. Let me ask you this. Does it change your perspective on existence knowing that at the center of our galaxy, there's a point where the fabric of reality breaks down, where the known laws of physics fail? Another area where our knowledge is limited involves the Sun, our closest star. You might think we understand the Sun well, and in many ways we do, but significant mysteries remain. One is the coronal heating problem. The Sun's surface has a temperature of about 6,000 degrees Celsius. But the corona, the Sun's outer atmosphere extending millions of kilometers into space, has a temperature of over 1 million degrees Celsius. How can the atmosphere be hundreds of times hotter than the surface below it? This violates our usual experience that things get cooler as you move away from a heat source. The answer involves magnetic fields. The sun's surface is covered with complex, constantly changing magnetic field structures. When these field lines reconnect and snap, they release energy that heats the corona. But the details of this process are still being worked out. NASA's Parker Solar Probe, launched in 2018, is flying closer to the sun than any previous spacecraft, passing through the corona itself to study the environment directly. Data from this mission is helping us understand coronal heating, solar wind acceleration, and other solar mysteries. Another solar mystery involves the solar cycle. The sun's magnetic activity waxes and wanes on an 11-year cycle, with the number of sunspots, solar flares, and coronal mass ejections rising and falling. But we don't fully understand what drives this cycle or why it's 11 years. Moreover, the cycle isn't perfectly regular. Sometimes it's stronger, sometimes weaker. And occasionally, the sun seems to enter extended periods of low activity, like the Maunder minimum in the 1600s, when very few sunspots were observed for about 70 years. This period coincided with the Little Ice Age in Europe, though it's unclear if the connection was causal. Predicting solar activity is important because space weather can affect satellites, power grids, and astronauts. But our predictive ability is limited by our incomplete understanding of the sun's internal dynamo that generates its magnetic field. If we don't fully understand our own star, a relatively simple and stable one, imagine how much we don't know about other types of stars and the exotic stellar remnants they leave behind. Let's consider the question of whether physical constants and laws of physics have changed over time. We assume that the speed of light, the gravitational constant, the mass of the electron, and other fundamental values have been the same throughout history. But is this assumption correct? Some theories suggest that constants might vary. String theory, for example, allows for the possibility that what we perceive as constants are actually determined by the configuration of extra dimensions, and these configurations might change. Astronomers have searched for evidence of changing constants by studying light from distant quasars that passed through clouds of gas billions of years ago. By analyzing absorption lines in this light, they can measure physical constants as they were billions of years ago and compare them to today's values. Most studies find no evidence of change, but a few claim to have found tiny variations in the fine structure constant, a number that characterizes the strength of electromagnetic interactions. These claims are controversial and not universally accepted, and if real, the variations are incredibly small, less than a few parts per million. But even the possibility that constants might vary is profound. If constants can change, then the laws of physics might be different in different places or times, and our understanding of the universe would need major revision. Similarly, there's the question of whether the laws of physics could have been different. Why does nature obey these particular laws and not others? Is there something that requires the laws to be what they are? Or is it arbitrary or contingent on initial conditions we can't access? Some physicists hope for a theory of everything, a final theory that explains all forces and particles and shows that the laws of physics had to be this way, that no other universe is mathematically consistent. Others think we'll never find such a theory and that the laws are simply what they are, with no deeper explanation. These questions border on philosophy, but they highlight the limits of scientific explanation. Even if we someday understand every particle, force, and phenomenon in our universe, we might still be left wondering why the universe is this way rather than some other way. Let's talk about planet formation, a process we once thought we understood, but that continues to surprise us. Our solar system has a particular structure. Small rocky planets close to the sun, gas giant planets farther out, and icy bodies in the outer reaches. For a long time, we assumed this was typical. Then, starting in the 1990s, we began discovering exoplanets, planets orbiting other stars. What we found was astonishing diversity. Hot Jupiters, gas giant planets orbiting closer to their stars than Mercury orbits the Sun. Super-Earths, rocky planets more massive than Earth but smaller than Neptune, a type of planet that doesn't exist in our solar system. Planets on wildly eccentric orbits. Systems where multiple planets orbit closer to their star than Earth is to the Sun. Rogue planets drifting through space without a star. This diversity challenges our models of planet formation. We thought planets formed in a disk of gas and dust around a young star, with rocky planets forming close in where it's hot and icy/gas planets forming farther out where it's cold. But hot Jupiters can't have formed where we find them. They must have formed farther out and migrated inward. How? Through gravitational interactions with the disk or with other planets. We're still working out the details. We've also found that planetary systems can be dynamically unstable. Planets can gravitationally scatter each other, ejecting some into interstellar space while others plunge into their star. Our solar system appears relatively stable and orderly, but that might be the exception rather than the rule. Understanding planet formation is crucial for understanding whether Earth-like planets are common or rare, which affects the likelihood of finding life elsewhere. Another mystery is the origin of Earth's water. Earth is a wet planet, with vast oceans covering most of its surface. But where did the water come from? Earth formed close to the Sun where it was too hot for ice to exist, so the water must have arrived later. Perhaps from comets, icy bodies from the outer solar system that bombarded early Earth. Perhaps from asteroids that formed farther out and contained water ice. When we analyze the isotopic composition of Earth's water and compare it to comets and asteroids, the match isn't perfect with either source. This suggests Earth's water might have come from multiple sources or from types of objects we haven't sampled well. Understanding Earth's water is important because water is essential for life as we know it. If we can figure out how Earth got its water, we can better assess how common watery, habitable planets are in the universe. These might seem like details, but they're puzzles that reveal gaps in our understanding of planetary science, gaps that we're actively working to fill. Now let's consider a question that's both scientific and existential. Why does the universe appear fine-tuned for life? We've already discussed how the fundamental constants seem precisely calibrated to allow complexity and life, but the fine-tuning goes beyond just constants. The initial conditions of the Big Bang had to be set with extraordinary precision. For example, the density of the early universe had to be almost exactly the critical density that balances expansion against gravitational collapse. If the density had been even slightly higher, the universe would have recollapsed in a big crunch before stars could form. If it had been slightly lower, the universe would have expanded too fast for matter to clump into galaxies. The actual density was within 1 part in 10 to the power of 60 of the critical value. That's like balancing a pencil on its point and having it remain balanced for billions of years. Similarly, the distribution of matter and energy in the early universe had to be smooth but not too smooth. If it had been perfectly uniform, no structures would have formed. If it had been too lumpy, everything would have collapsed into black holes. The actual distribution was just right to produce galaxies, stars, and planets over billions of years. Inflation theory explains some of this fine-tuning by showing that a period of exponential expansion would naturally produce a universe that's flat and smooth with small density fluctuations. But inflation itself requires fine-tuned initial conditions to start, so it pushes the problem back rather than fully solving it. The multiverse offers one explanation. If countless universes exist with different properties, it's not surprising that we find ourselves in one of the rare ones that allows life. But as we discussed, the multiverse is controversial and might be untestable. Another possibility is that there's some deep physical principle we don't know yet that requires the universe to have these properties. Perhaps there's a theory that shows the constants and initial conditions couldn't have been any other way. Or perhaps the universe actually isn't fine-tuned, and we're suffering from a lack of imagination. Maybe life could exist with very different physical laws, and we just can't envision it because we only know carbon-based life in our particular universe. These questions touch on deep issues in philosophy of science. What counts as a satisfying explanation? Is the anthropic principle, the idea that we observe properties compatible with our existence because we couldn't exist otherwise, a legitimate scientific explanation, or a cop-out. Here's a question for you. If you discovered definitive proof that our universe was designed or created intentionally, how would that change your worldview? Alternatively, if you discovered definitive proof that our universe is one of infinite random universes with no deeper meaning, how would that change how you live your life? Let's discuss another frontier of ignorance, the interiors of planets. We know a lot about Earth's surface, but our direct knowledge of the interior is limited. The deepest hole ever drilled, the Kola super-deep borehole in Russia, reached about 12 kilometers deep, barely scratching the surface of a planet with a radius of over 6,000 kilometers. Everything we know about Earth's deep interior comes from indirect methods like seismology, studying how earthquake waves travel through the planet. We know Earth has a crust, mantle, outer core, and inner core, each with different compositions and properties. But many details remain uncertain. What's the exact temperature at the core mantle boundary? How much heat is generated by radioactive decay versus leftover from Earth's formation? How does the mantle convect, driving plate tectonics? What's the composition and structure of the inner core? Recent studies suggest the inner core might have its own inner core, a distinct region at the very center with different properties. But this is still being investigated. For other planets, our knowledge is even more limited. We can measure mass, radius, and rotation, and make inferences about interior structure, but there's a lot of uncertainty. Jupiter's interior is thought to contain metallic hydrogen under immense pressure, a state of matter we can barely create in laboratories. Neptune and Uranus might contain layers of exotic superionic water ice, where oxygen atoms are locked in a crystal lattice while hydrogen atoms flow freely like a liquid. These aren't just academic curiosities. Understanding planetary interiors is crucial for understanding how planets form, evolve, and generate magnetic fields that protect against harmful radiation. Earth's magnetic field, generated by convection in the liquid iron outer core, has reversed many times in the past, with north and south magnetic poles swapping. We know this from studying magnetic minerals in rocks that recorded the field direction when they formed. These reversals happen irregularly, sometimes millions of years apart, sometimes much more frequently. We don't fully understand what causes them or whether we can predict when the next one will occur. A magnetic reversal wouldn't be catastrophic. The field doesn't disappear. It just becomes more complex and weaker for a period before reestablishing with opposite polarity, but it could affect technology and expose the surface to more cosmic radiation. The point is, even our home planet holds mysteries in its depths. Another area of profound ignorance involves the nature of biological life and its origins. Astrochemistry and astrobiology are relatively young fields, but they've made fascinating discoveries. We know that organic molecules, the building blocks of life, are common in space. Amino acids have been found in meteorites. Complex organic molecules exist in interstellar clouds. The raw materials for life are abundant. But how did non-living chemistry become living biology? How did the first self-replicating molecules form? Did life arise in a primordial soup of chemicals struck by lightning, as classic experiments suggested? Did it start in deep-sea hydrothermal vents? Did the first replicators use RNA or some other molecule? Did life start once in a single location, or did it emerge multiple times independently? These questions remain unanswered. We can study modern life and work backwards, inferring what the earliest organisms might have been like, but the further back we go, the more speculative it becomes. The actual transition from chemistry to biology happened billions of years ago, and any direct evidence has been erased by geological processes. Some scientists propose panspermia, the idea that life originated elsewhere in the universe and was transported to Earth on meteorites or comets. This is possible. Microorganisms can survive in space for extended periods, but it just moves the question of life's origins to another location. Finding life elsewhere in the universe, even simple microbial life, would be revolutionary. If we discovered that life arose independently on Mars or Europa or Enceladus, It would suggest that life is common in the universe wherever conditions are suitable. If we found life and it had a completely different biochemistry than Earth life, using different molecules or different genetic code, it would prove that life can arise in multiple ways. Conversely, if we explore the solar system thoroughly and find no life anywhere else, that would suggest life might be rare, perhaps unique to Earth. This would have profound implications for our place in the cosmos. The search for biosignatures, signs of life, on exoplanets is one of the most exciting frontiers in astronomy. The James Webb Space Telescope and future missions are analyzing the atmospheres of rocky exoplanets, looking for gases like oxygen, methane, or phosphine that might be produced by living organisms. But interpreting these observations is tricky because non-biological processes can also produce these gases. We need to be careful not to claim discovery of life based on ambiguous evidence. The question of whether we're alone is tied to questions about what life is, how it starts, how common habitable environments are, and whether intelligence and technology inevitably emerge given enough time. These are all areas where our knowledge is limited. Imagine if tomorrow we detected a clear, unambiguous signal from an extraterrestrial civilization. How would that change humanity? How would it change you? Let's discuss one more profound mystery. Why is there something rather than nothing? This is perhaps the deepest question of all. Existence itself is strange when you think about it. Why does anything exist? Why is there a universe at all? Why are there laws of physics? Why is there space and time? Some argue this question is beyond the scope of science, that science can explain phenomena within the universe but not why there's a universe in the first place. Others argue that physics might ultimately answer this question. Lawrence Krauss, in his book, A Universe from Nothing, argues that quantum mechanics allows the universe to arise from a quantum vacuum, a state with no matter or energy but still governed by physical laws. Virtual particles constantly pop in and out of existence due to quantum fluctuations, and perhaps the entire universe is a large-scale version of this phenomenon. But critics point out that a quantum vacuum isn't truly nothing. It's a state described by quantum field theory, which presupposes the existence of space-time and physical laws. So this doesn't fully answer why there's something rather than nothing. Leibniz, the philosopher and mathematician, asked this question centuries ago and proposed that there must be a sufficient reason for existence, something that explains why reality is this way. But he never identified what that sufficient reason might be, and it's unclear if such a reason exists or can be found. Some physicists speculate that perhaps nothingness is unstable, that given quantum mechanics, a state of absolute nothingness would inevitably fluctuate into something. But this raises the question of why quantum mechanics exists at all. These are questions at the boundary of science, philosophy, and perhaps theology. They might have answers, or they might be questions that we'll never resolve. But they highlight just how much mystery remains at the foundation of existence. Throughout this journey, we've explored mysteries ranging from the very large, the fate of the universe and the nature of dark energy, to the very small, the quantum realm and the fundamental particles and forces. We've discussed mysteries about time, space, consciousness, and existence itself. We've seen how every answer we find seems to raise new questions, how the frontier of knowledge constantly expands outward, revealing new territories of ignorance. This might seem frustrating or even depressing. We've spent centuries doing science, built powerful instruments, developed sophisticated theories, and yet we're surrounded by unknowns. We don't know what most of the universe is made of. We don't know where we came from or where we're going. We don't know if we're alone. We don't know what consciousness is or why the laws of physics exist. But there's another way to look at it. We live in an extraordinary time. Many of these mysteries have only recently been discovered. A century ago, we didn't know about the Big Bang, dark matter, dark energy, black holes, quantum mechanics, or exoplanets. We've learned an incredible amount in a cosmically brief period of time. And we're actively working on these mysteries. Telescopes in space and on Earth are gathering data. particle accelerators are probing the fundamental nature of matter. Gravitational wave detectors are listening to space-time itself. Rovers are exploring other worlds in our solar system. Theoretical physicists are developing new frameworks to understand quantum gravity and the earliest moments of the universe. Some of these mysteries might be solved in your lifetime. Perhaps we'll detect dark matter particles and figure out what they are. Perhaps we'll develop a working theory of quantum gravity. Perhaps we'll find life on another world. Perhaps we'll discover something completely unexpected that revolutionizes our understanding. And that's the beautiful thing about science. It's never finished. There's always more to learn, always deeper questions to ask, always new frontiers to explore. The universe is far stranger and more wonderful than we imagined, and every discovery reveals new layers of mystery. So when you look up at the night sky, remember that you're seeing just a tiny fraction of what's out there. The photons entering your eyes left distant stars years or centuries or even millions of years ago, carrying information across the cosmic void. You're seeing the past, and you're seeing only the visible part of a universe that's mostly invisible. Remember that you're made of atoms forged in the cores of ancient stars that exploded billions of years ago, scattering their material into space where it eventually coalesced into planets and people. You are, quite literally, stardust, the universe made conscious, looking back at itself and wondering. Remember that standing on the surface of this small rocky planet, you're part of something incomprehensibly vast and ancient, a cosmos that's been evolving for nearly 14 billion years and will continue for trillions more. And remember that despite all we've learned, despite our telescopes and equations and theories, we've barely begun to understand it all. The universe is still full of secrets, still capable of surprising us, still mysterious. The story of the cosmos is not a story that ends with all questions answered and all mysteries solved. It's an ongoing narrative, and you're part of it. Every time you ask a question about how things work, every time you wonder why the universe is the way it is, you're participating in the same quest that has driven humans throughout history, the quest to understand our place in the grand scheme of things. Perhaps some mysteries will never be solved. Perhaps there are truths about reality that are forever beyond our capacity to understand, limited as we are by our senses, our instruments, and our minds. Or perhaps, given enough time, we'll figure it all out, understanding the universe completely from the largest scales to the smallest, from the beginning to the end. We don't know which it will be, and in a way, that uncertainty is itself part of the wonder. The future is open. Discovery awaits. The universe is still revealing itself to us, one mystery at a time. What will we learn next? What will tomorrow's telescopes see? What theories will future physicists develop? What questions will the next generation ask that we haven't thought of yet? These questions don't have answers yet, but they will. Or they'll be replaced by even deeper questions that take us further into the unknown. And that's the point. The journey of discovery doesn't end. As long as humans exist and look up at the stars with curiosity and wonder, asking why and how and what if, the quest to understand the universe will continue. We are explorers on the shore of a cosmic ocean, having just begun to venture into its depths. The universe is vast. It's ancient. It's beautiful. It's terrifying. It's mysterious. And it's ours to explore, to study, to wonder about, for as long as we persist as a species. So the next time you find yourself under a clear night sky, take a moment. Look up at the stars. Think about all that we know and all that we don't. Think about dark matter holding galaxies together, dark energy pushing the universe apart, black holes warping space-time, quantum particles existing in multiple states until observed, the cosmic microwave background carrying echoes of the Big Bang, gravitational waves rippling through space, distant worlds orbiting alien suns, and all the other marvels we've discovered. Then think about all the mysteries that remain. Think about what we still don't know, and may never know, about the universe we call home. And ask yourself, what role will you play in this ongoing story of discovery? What questions will you ask? What will you wonder about? What mysteries call out to you? Because the universe isn't just something out there, separate from you. You're part of it. You're the universe experiencing itself, questioning itself, trying to understand itself. And in that sense, every mystery about the cosmos is also a mystery about you. Every question about the nature of reality is a question about your own nature, because you are made of the same stuff as stars and planets, governed by the same laws, emerging from the same cosmic history. We don't have all the answers. We may never have all the answers. But we have the ability to ask questions, to wonder, to explore, to discover. And in a universe full of mystery, that might be the most remarkable thing of all. The cosmos waits. The mysteries endure. And the journey continues, into the unknown, into the darkness, seeking light, seeking understanding, seeking truth. What wonders await us in the depths of space and time? What secrets does the universe still hold? What revelations will change everything we think we know? We don't know yet, but we'll keep looking. We'll keep questioning. We'll keep exploring. Because that's what we do. That's who we are. We are the species that looks up at the night sky and asks why. We are the ones who build telescopes and particle accelerators, who develop theories and test them against reality, who refuse to accept ignorance as a permanent condition. The universe has given us consciousness, curiosity, and the ability to understand, at least partially, the cosmos that created us. What we do with these gifts, how far we can go in our quest for knowledge, what we'll ultimately discover about the nature of reality, remains to be seen. The mysteries remain. The questions persist. The unknown beckons. And somewhere out there, in the vast darkness between the stars, in the quantum foam of space, in the depths of black holes, in the far future or the earliest moments of the Big Bang, in dimensions we can't perceive or in other universes we can't reach, answers wait to be found. Or perhaps they don't. Perhaps some questions have no answers. Perhaps reality is fundamentally mysterious, irreducibly strange, forever beyond complete comprehension. But we won't know until we look. We won't know until we try. We won't know until we venture further into the unknown, armed with curiosity and guided by reason, seeking truth wherever it leads. The universe is full of things astronomers still don't know. And that's not a failure. It's an invitation. An invitation to wonder, to explore, to discover. The story isn't over. It's just beginning. And you're part of it, here, now, alive in a universe full of mystery and wonder, capable of asking questions that reach into the very heart of existence itself. What will you discover? What will you wonder about? What mysteries will captivate your imagination? The cosmos awaits your curiosity. The unknown beckons. The journey continues. And somewhere, in the darkness between galaxies, in the quantum uncertainty at the heart of reality, in the far reaches of space and time, the universe keeps its secrets, waiting for the day when we finally understand. That day may come, or it may not. But the quest itself, the journey of discovery, the drive to understand, that's what makes us human. That's what makes us remarkable. We are, each of us, made of stardust and mystery, existing briefly in a cosmos we barely understand, reaching out with our minds and our instruments to grasp truths that have existed for billions of years before us and will persist for billions more after we're gone. And in that reaching, in that questioning, in that ceaseless drive to know and understand, we touch something eternal, something profound, something that connects us to the deepest nature of reality itself. The mysteries remain. The questions echo through space and time. The universe keeps its secrets, for now. But we keep looking. We keep wondering. We keep reaching for understanding. Because that's what we do. That's who we are. We are the universe trying to understand itself. And the journey, the quest, the search for truth and meaning in a cosmos full of mystery, that journey continues, one question at a time, one discovery at a time, one moment of wonder at a time. The night sky calls to us. The mysteries beckon. The unknown awaits. And we, brief sparks of consciousness in an ancient and vast cosmos, continue our journey into the depths of reality, seeking answers to questions that may have no end. This is our story. This is our quest. This is who we are. Seekers of truth in a universe full of mystery. Explorers of reality in a cosmos beyond comprehension. Questioners of existence in a reality stranger than fiction. The mysteries remain. And so do we, wondering, questioning, exploring, seeking. Forever reaching toward understanding, even if complete understanding forever remains beyond our grasp. Because the journey itself, the quest for knowledge, the drive to understand, that's what gives meaning to our brief existence in this strange and wonderful universe. The cosmos is full of things we don't know, and that's beautiful, because it means there's always more to discover, always new frontiers to explore, always deeper questions to ask. The universe is not finished revealing itself to us, and we are not finished trying to understand it. The journey continues into mystery, into wonder, into the unknown.